here's the schedule for today. We'll finish up and discuss these equations and how we use them. Then you have your first real physics assignment today. Tomorrow we'll talk about gravity and how that plays into it. And then Wednesday is kind of a summative, kind of tie up loose ends, do a lab. Thursday we'll review. Friday will be the first really big physics test. Okay, so that's the schedule for the week. And then after that we'll start into forces. And problem is we have we'll start forces and this has never happened. Of course, it's never had it taught in the pandemic either. But usually we finish before spring break. We have a nice break, and then we start back up after spring break. Well, unfortunately, this one, spring break, is actually going to interrupt the forces unit. So we'll start forces and then we'll have a week off for spring break, and then we'll finish up after that. So that's going to present a little bit of a challenge, but we shall overcome. Okay, so on Friday we came up with these equations that V equals V naught plus AT, distance equals 1/2 V plus V naught time, distance equals 1/2 AT squared plus V naught time. Okay? Now, the whole key to this, and there's one other one which we'll get to today, this V squared equals V naught squared plus 2AD. The beauty of this test coming up on Friday is that there are only 4 equations to choose from. Okay? You just have to know how to use it. Literally, there are only 4 equations. But I beg of you, the worst thing that you can do when you get into these problems is play the equation game. And you go, oh, what equation? Sorry, hold on. Oh, I did start it. Never mind. I get really paranoid if I'm not sure that camera is going, because I've taught entire lessons and then realized that the camera wasn't recording, and then it's just then you got to go back and redo it. Okay. All right. And it's Monday. I just wanted to make sure. All right. So the worst thing that you can do is say, oh, what equation am I going to use? It's the worst thing that you can do. The best thing that you can do is look at the big picture. So here's what we're going to do. Here's how you can use these equations. So I'm going to have Brooke with her phone. And I've got this cart, right? And I've got a fan that I can put on here, right? And I can provide a force. Okay, so the fan's going to be on high, boom, we're going to measure this force. So I'm going to have it like this, right? I'm going to turn this on and let go of it. And we'll make it go. So first off, Shivani, what's the initial velocity of the cart going to be? 0. Okay, so this is going to be a key thing. The cart's going to start at 0. Okay? Now, a lot of times what you will see, either the cart will start at 0 and it gets accelerated, okay? For example, you're going to have a situation on your assignment where you have a fighter jet that's being launched off an aircraft carrier. Okay, it's going to start at 0 and then it's going to speed up. Or, what you also see a lot is where a car is moving and then you stop it. Okay, and then you say, okay, well, if it's going to stop, what's the final velocity going to be? So a lot of times, not always, okay, but a lot of times either your initial velocity is 0 or your final velocity is going to be 0. Not always, but that's how it plays out a lot. So even with this, if I turn this on, right, and I get it moving and I push it, okay, it was moving and then it came to a stop, right? Or I can have it at rest and then it begins to move, okay? But not always, but a lot of times that's how it'll play out. So once I turn on this fan and I make it move, what are some physical quantities that I can measure to use in these equations? Because what I want to find is the acceleration of the system. Matt, what are some things that I can measure?
The distance it travels.
Okay, I can measure how far it goes. So I can say, okay, well, the front edge of this cart is at 100 centimeters, okay? And then I could turn it on and I could let it go until the front edge is at 60, okay? So I'd say, okay, it's going to travel a certain distance. Now, Shivani also said that the initial velocity was 0. That's not something that I need to measure, but I'm clever and I'll go, okay, hey, the initial velocity is going to be 0. Now, Brooke, what can you measure? She can measure time, okay? So, if I know time, and I can measure how far it goes, I ultimately can find the acceleration. Now, the thing is that you want to decide, okay, if you look at V naught, V dat, okay? Now, there's a couple of things that you want to look at. First off, in these equations, do I need the mass of the cart? No, right? You can't plug the mass of the cart into these equations if you tried, okay? It's not there. I can't plug in the fact that, oh, it's green, okay? Can't plug that into the equation either. It's irrelevant. So one of the things that you have to begin to focus on is what is a factor in these equations and what is not a factor. In all of these equations, in every problem I'm going to give you on this test on Friday, on all of the assignments that I'm going to give you, for now, I am not going to give you the mass of the cart because it doesn't matter, okay? It does not matter. You can't plug them into the equation if you try. Now, when we get into force, F equals ma, the next unit, then we're going to have to know the mass. But for now, the mass of the object doesn't matter. It's not there. It's not a factor, okay? So, Brooke, get your phone out. So we're going to start it at 100. And I'm going to tell you to stop when it crosses the 60 centimeter mark, so we're going to go 40 centimeters, okay? Actually, let's go 50. That'll make the math easy, okay? So you ready? So 3, 2, 1, go. Stop. So how much time did it take?
3.84.
3.84 seconds, okay? So we had a distance of 0.50 meters. We had an initial velocity of 0. And we don't know the acceleration. Okay, so Karen, which of these three equations do I want to choose then to find the acceleration of the cart?
The third one?
Okay, beautiful. Why?
Because we don't know the final velocity, and that one doesn't have the final velocity. And
Yeah, I could use this to potentially find it, but I don't know what the final velocity is. So I wouldn't know the final velocity, nor would I know the acceleration. So this one won't do me any good because I'd have two variables with one equation. Okay, it's dead in the water. What about this one? Would I want to use this to find acceleration? No. Why? I don't know the time, and acceleration isn't even in here either, okay? So I can't do that, right? What now? I got this one. Hey, I'm all over this one. Now, here's the deal. The initial velocity is 0, so this whole thing drops out, right? So that V naught is going to go to 0. Now, what I want to do, and again, I beg of you, get in the habit of solving these equations. Oh, I want to multiply by 2, I'm going to divide by t squared. So somebody get out a calculator. So I'm going to take 2d divided by t squared is going to equal my acceleration. So I'm going to take 2 times a half meter divided by 3.84 seconds squared. So Matt, what'd you get?
0.067.
0.067 meters per second squared. Okay? Not very much. Certainly that's a lot less than when I drop something and I get an acceleration of 9.8 meters per second squared. Okay? It's a little fan, right? It's kind of cool, right? Okay? But it's just, you don't get a huge acceleration. So this is just a situation where you can use these equations to figure out what's going to happen. Now, Ms. Pfeiffer, what would the velocity time graph look like for this situation? Where would it start?
0.
Okay, then what?
And then base.
So would it curve up like this?
Yeah.
So you're going to say my velocity time graph is going to go something like this.
It's not constant, so yeah.
Okay? Everybody cool with this curved line for your velocity time graph? Shivani?
Doesn't it have to go like this? Because it like can't go that fast.
So you're going to say it's going to go like this.
Yeah.
Okay? So let's just complete the lip curve. Let's just go ahead and throw in the middle curve as well. So we have A, B, and C. So there's 5 of you, right? So how many vote A? Shivani, you have to vote it.
Oh, I forgot.
Okay, you're the one that said you wanted this. Okay, right? How about C? 1, 2, 3. How about B? There's one that votes on the, so we have some on the A train, some on the B train, some on the C train. Now there's this big sign behind you that says F equals ma, right? What was creating the force to make the cart move? The fan. Was the fan at the same speed the entire time? Yes. Okay. So here's what happened, right? I had it like this, the fan got up to speed, I let go of it. Fan was producing the same force all the time. So if the force stays the same, and the mass stays the same, what has to happen to the acceleration? It has to stay the same. So it's the only graph that shows the same acceleration all the time. B. Okay? Again, you all in your heart of hearts, you're going, it's going faster! This line has to curve! Okay? Because I blame Nike. Okay? Nike has done more to ruin physics than anybody. It's B, right? Because here's the deal. If you say it's A, then you're saying the acceleration is decreasing as it goes. If you're choosing C, you're saying the acceleration is getting faster as it goes, which the only way that can happen is if the force is getting bigger. Okay? It's boring, but B is the correct choice. Okay? It's what we call uniform acceleration. So here's the deal. Your velocity time graph has to be a straight sloping line, because that's the only way it's a linear function, where it's mx plus b, which is the only way we can use v equals v naught plus at. Because if your slope is changing, that means your acceleration is changing, which means it's not a linear function then. Okay? So any velocity time graph is going to be a straight sloping line. Now, what's the position time graph? Now, the position time graph is where you can do the Nike curve, right? So what's the position time graph going to look like? I'll give you 3 choices. Bing, bing, bing. Upper lip, middle lip, lower lip. Brooke, which one? A, B, or C? Upper lip, lower lip, middle lip. Upper, middle, lower.
Lower.
Beautiful. Why? What does the slope of a position time graph give you? Was the cart going faster as it moved?
No.
Really? The cart wasn't going faster as it moved.
I thought it was constant.
Okay, your acceleration is constant, but remember.
Oh, okay. Yeah, it was going fast.
Yeah, it was going. Mike, remember, acceleration is not how fast you're going. Your acceleration is the rate at which your velocity changes. Okay? So, yes, I did have a constant slope on my velocity time graph, which indicates that I have constant acceleration. This is going to be a curved line, right? Because this is showing the object going faster and faster and faster. Okay? So, it's going to be, this one's going to be a curved line. So that, because it's showing as a quadratic function, it's going faster. Okay? Now, come back here. Now, their time was 3.84 seconds. Okay? All right? So, Karen, how does that half a meter, which is how far it went, play into this velocity time graph?
Because that was the distance.
Yep.
And define the area underneath, that's the displacement.
Yes.
And you need the distance?
Yeah, well, that's what it is, right?
Yes.
So that 0.5 meters would be this area underneath this triangle. Okay, that's it. That's the area. So that's 0.5 meters. Now, at this point, we could figure out how fast the cart was going. Because we know this is 3.84 seconds, right? We know the slope of the line is 0.067 meters per second squared, right? We got that number. So here's what you have to understand, okay? You have to understand what acceleration is. If you start at 0, at the end of the first second, you're going to be going 0.067 meters per second. So for every second that goes by, your velocity is going to increase 0.067. So at the end of 1 second, you're going to be going 0.067 meters per second. At the end of the second, you're going to be going twice as fast. At the end of 3 seconds, you're going to be going 3 times as fast. Okay? Because your velocity changes as a linear function of time. Okay? So if we want to figure out how fast it's going at the end of 3.84 seconds, just go, oh, V equals V naught plus AT. Remember, your V naught is your y-intercept. Oh, it started at 0. Oh, okay, cool. So that's just going to be 0. And I'm going to have 0.067 meters per second times, so take 0.067 meters per second times 3.84 seconds.
0.26.
0.26 meters per second. So the end of 3.84 seconds, it's going to be traveling 0.26 meters per second. Now, this is where the position time graph correlates with this velocity. Because remember, okay, if you go back to what Brooke said, the slope of a position time graph gives you the velocity. So if you came out here at 3.84 seconds and you drew a tangent line, that would have a slope of 0.26 meters per second, because that's how fast it's going at that point. If you went to 1 second and drew that tangent line, it started at 0, at the end of 1 second, it's going to be going 0.067 meters per second. So at the end of 1 second, it's going to be traveling 0.067 meters per second. So this line is continuously getting steeper. Your tangent lines are becoming steeper because you're going faster. Yes?
So in a velocity time graph, it's always going to be like straight unless we have different forces.
Exactly. That's it. Now, so if you look at this, this was like, let's say that you did this, right? Okay? And you had it like at low speed, right? And then you shift gears and you go to high speed. Then what would happen is that you would have like a shallow slope on your velocity time graph because you had a smaller acceleration. But then when you kicked it into high gear, then it would become a steeper slope because then you've changed the force. So the only way to change the slope of your velocity time graph is to change your acceleration. The only way you can change the acceleration is if you change the force. Got it? Good? Brand? Okay. So here's one thing I want you to look at. So let's say that you've got a carrot car, just like kind of like what we had here, right? And let's make the math a little bit easier. Let's say the acceleration is 4 meters per second squared. And we're going to look at 1 second, 2 seconds, 3 seconds, and 4 seconds. So I got the car. It's going to accelerate a lot faster than this did. Okay, it's going to accelerate at 4 meters per second squared. So here's what I want to figure out. I want to figure out at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds. I want to figure out how fast it's going at the end of each of these seconds, okay? And then I want to figure out how far it's traveling at the end of each second, right? So I want to know how fast it's going, and I want to know how far it's traveled, okay? So I want to draw a velocity time graph on a position time graph. So Shivani, where's my velocity time graph going to start?
0.
Yeah, because the car is at rest, right? So it's going to start at 0. So Shivani, since you're on a roll with this, how does that 4 meters per second squared, which is my acceleration, how is that going to fit with this velocity time graph?
It's going to be 4 meters per second at 1 second. And
Beautiful,
it's gonna
okay?
go-
Fantastic, okay? Fantastic answer. So at the end of 1 second, the car is going to be going 4 meters per second. At the end of 2 seconds, it's going to be going 8. So that's going to be the slope of the line, right? Okay? Fantastic. So this is going to be the slope of the line. Why does it not do that all the time? Okay? 4 meters per second squared. At the end of 1 second, it's going to be going 4 meters per second. At the end of 2 seconds, it's going to be going 8. At the end of 3, okay? So, right? So this is just going to go 4, 8, 12, 16. Now, but you're going, oh, Mr. Burkamp, I like equations. I live for equations. I'm happy for you, okay? So if you want to go, I want to use equations. Okay, well, fine. You have V equals V naught plus AT. Now, here's what's important. This is a slope-intercept form for a linear function. Okay, this is important. It's a linear function. Velocity changes as a linear function of time because it's AT, right? So, if you like equations, you'd take 4 meters per second squared times 1 second, and you would get 4 meters per second. At the end of 2 seconds, I would plug in 2, and I would get 8. I would plug in 3, and I would get 12. I would plug in 4, and I would get 16. Okay? So if you like equations, go with this. Okay? Same idea. Now, so here's my question. So I got those. Okay? So velocity changes as a linear function of time. Okay? It's important because it's just acceleration times time. Now, here's the next question. I want to know how far it's traveled at the end of 1 second. So, Kara, could I do this? I know at the end of 1 second, I'm going 4 meters per second. So to figure out how far it's gone, could I take 1 second and multiply that by 4 meters per second and get 4 meters? Why not? It's simple. It's 1 second, I'm going 4 meters per second. Boom, here you go.
It sounds too easy. I know that's not right. I just know it's not.
You have trust me, gut feelings in life are important. Okay? And you're right, I can't do that. Okay? It's horrible, I can't do that. Because here's the deal. If you did that, you're saying, oh, distance equals velocity times time. Now, what did I tell you? What's the only time you can use that equation is if you have what type of velocity?
Constant.
Constant velocity. Okay? If you have constant velocity, you're not accelerating, and this would be a horizontal line. Okay? So, if you ever, in this unit, on this assignment, any of these assignments coming up on the test, if you find yourself using this, stop. Don't. Okay? Under no circumstances in this acceleration unit are you going to use this unless I explicitly, and I mean I explicitly tell you, hey, this thing is moving at a constant velocity. Okay? Unless I explicitly tell you that, do not use this equation. Okay? Don't do it. Bad. It's going to be a train wreck. Okay. Now, there's a couple of ways that we can figure out how far it went. We know at the end of 1 second, it's traveling 4 meters per second. So this looks like a triangle, right? So at the end of 1 second, right? Matt, how do I find the area of a triangle?
Base and height.
So I've got a base of 1 second, right? I've got a height of 4 meters per second. So I'm going to have 1 times 4, and then I'll take half of that, and I'm going to get 2 meters, right? Okay? So if you like triangles, you go, Mr. Burkamp, I was like the triangle area champion in 3rd grade. Okay, we had a competition of who could calculate the areas of triangles best in 3rd grade. I won. I've got a little triangle trophy. Good for you. Okay? Put that in your college application. So, I was the triangle king. Okay, you could do that. Okay, and you could get 2 meters. Now, I don't recommend that. And here's the reason why. Here's why I don't recommend that you do that. Even though the math is simple, here's the problem. If I screwed up finding that velocity at the end of 1 second, okay, so in other words, because I'm using a value that I have found, if that 4 meters per second is wrong, my displacement is going to be wrong. Okay? So you want to avoid using derived values as long as you can. You want to work off values that are given to you in the problem as long as you can. Now, you are going to run into situations where you don't have a choice. You're just going to have to take the leap of faith and use values that you've already found. But if you can put that off as long as you can and work off known values, that's the approach that you want to take. Okay? So what I would recommend, if it were me, I'd use that distance equals 1/2 AT squared plus V naught time. And here's the reason why. My initial velocity is 0. Okay, don't have to worry about that. My starting at rest, okay, velocity time graph starts at 0. Don't have to worry about that. I got my acceleration, which was given, 4 meters per second squared, times 1 second squared, and oddly enough, you're still going to get 2 meters. I would prefer this because I know my acceleration and I know my time. Okay? Now, here's what's important. Okay? Here's one of the most important things that I want to stress to you. And this is the difference between these two equations. Okay? So, velocity changes as a linear function of time because this is acceleration multiplied by time. Distance changes as a quadratic function of time because it's t squared. Okay? So if I double the time, I double my velocity because it's just acceleration times time. So at the end of 2 seconds, I'm going to be going 8 meters per second. But this is t squared. So if I double the time, my displacement is actually going to go up by a factor of 4. Now let's make sure that that's cool. So if I go to the 2 second mark, right? So I'd have distance equals 1/2 4 meters per second squared times 2 seconds squared. And here's what you're going to do wrong. You mark my words. You're going to forget the square of the time. Okay? This is what you're going to do wrong. You sit there and go, oh, Mr. Burkamp, you won't do that. Yes, you will. You lie. Let's see what's going to happen. Now, I got 2 squared, which is 4. 4 times 4 is 16. Half of 16 gets me 8 meters. So, at the end of 2 seconds, I'd gone 8 meters. So look what happened. Notice I doubled the time. My distance went up by a factor of 4 because it's t squared. But if I double the time, my velocity just doubles. So my velocity doubles, but my distance goes up by a factor of 4 because it's t squared. Okay? Got that? Beautiful. Great. Grand. Now, if I go to 3 seconds, okay? At 3 seconds, I'm going to have 1/2 4 meters per second squared times 3 seconds squared. 3 squared is 9. 9 times 4 is 36. Half of that gets me 18 meters. Now, look what happens. I tripled the time, okay? I went from 1 second, I tripled the time. Notice that my distance traveled goes up by a factor of 9 because it's t squared. Oh, I tripled the time, it goes up by a factor of 9. So, Brooke, if I quadruple the time, my distance should go up by a factor of, what's 4 squared? Brooke, what's 4 squared?
16.
Yes. So if I triple it, my distance is going to go up by a factor of 16. I initially went 2. Guess what? That's going to be going at 32 meters. Okay? So this is one of the most important things you have to understand. Okay? I promise you I'm going to ask you this on the test. Velocity changes as a linear function of time. Position changes as a quadratic function of time. Now, here's where all of this fits together. Okay? So my position time graph is going to be a quadratic function, which is going to go like this. So at the end of 1 second, I'd gone 2 meters. Out here at the end of 4 seconds, I'd gone 32 meters. These lines are becoming steeper and steeper and steeper because of the fact that the object is going faster and faster and faster. So my position time graph, at the end of 1 second, if I were to find that slope, that would have a slope of 4 meters per second. At the end of 4 seconds, I was going 16 meters per second. That's going to be the slope of the line there. So you have to understand how these two graphs fit together. Okay? Got it? Good? Great. Okay. So, a lot of times how you're going to use this particular equation, distance equals 1/2 AT squared plus V naught time. So how this one plays out a lot is that you'll sit there and go, okay, here's a car, and I know that I'm going to have a distance of, I don't know, 20 meters and an acceleration of 5 meters per second squared. And I want to know how long it's going to take. So a lot of times, I just want to show you this because this is what you're going to, this works out well. You'll use this a lot. Where you're going to use this to like find the distance. And you'd say, okay, hey, the car is going to start at rest. So the initial velocity is 0. I know how far it goes. I know the acceleration. I don't want to solve for time. So I'm just showing you how this plays out. So that's going to drop out. So you'd have 2D over acceleration, and the square root of that is going to get you time. Okay? So I just want to make sure that everybody's cool solving this equation for time. Especially tomorrow when we get into gravity. Like I'm going to drop something, and I'm going to know how far it's going to fall. And I know the acceleration caused by gravity, and I want to know how long it's going to take for it to fall. So, I'm just kind of throwing that out there. Okay, now, stop, stand up, take a stretch. We've got one more big equation to go through. Stop this for a second. But you know, we're going to get through it, and it's
Or
going to be
two,
through.
so there's 3 weeks of this first term.
Okay. The thing I did by
Do you
engineering
have this week?
and the next week. No, next week.
And then 1 more week of the
Right,
10.
okay.
Okay.
So, a year minus 2 weeks.
So, here's the last of the equations. So, this is what's, over the years, this has become known as that equation. This is the only one that has a name, okay? So, and this has probably been that way for the past 5 or 6 years. A kid by the name of Nettie named it this equation, or named it, and then it's just stuck with it ever since. So this is the only one that's known as that equation. Now, here's what's different with that equation. So if you look at the other ones, V naught plus AT, distance equals 1/2 E plus V naught times time, distance equals 1/2 AT squared plus V naught time. What makes this one unique is that this is the only one that isn't dependent upon time, okay? All the other equations require time. So if you read a problem and you don't have time, don't flip out. Oh my God, I have to find time. This is why we have that equation, okay? So if you get into a situation where you read a problem and there's not time, this is your go-to equation, because it's the only one that's not dependent upon time, okay? Because some kids flip out, and they're going to go, oh, I'm going to take distance and divide it by velocity, I'm going to get time, and then I'm going to try and use this. No, bad, stop, okay? This equation exists for problems that don't involve time. So here's how this would play out. So let's say that here's a car, and you know that it's moving at 5 meters per second. So let's say that you're designing highways, okay? And you know that like you have like the acceleration, the merge lane, where you drive and then you merge into traffic. So let's say that you know cars, when they start, are going to be going at like 5 meters per second, which isn't all that fast. I mean, I'm old and I can run that fast, okay? And let's say that when you know when you merge into traffic, that it's going to be going, I don't know, 30 meters per second, okay? So that's the final velocity. And you know that cars will typically accelerate at 4 meters per second squared. Okay, so that's kind of going to be your average acceleration. You know, yeah, if you're a teenager with a hopped up car, that acceleration is going to be bigger than that. If you're grandma, right, it might be 2 meters per second squared. Okay, but on average, cars are going to accelerate at about 4 meters per second squared. So I want to know, how long do I build this acceleration lane so that this can happen? Okay, so if you look at that equation where you have v squared equals v naught squared plus 2ad, right? So I know everything but the distance. So, Miss Pfeiffer, how can I get distance by itself?
You can subtract initial velocity and then divide it by 2a.
Beautiful. So I'm going to have v squared minus v naught squared divided by 2a. That's going to give me my distance. Okay? So Matt, I just made up this problem, so wing this. So I'm going to have 30 meters per second squared minus 5 meters per second squared divided by 2 times 4 meters per second squared. So take 30 squared minus 25 divided by 8.
109.37.
109 point what?
0.375.
So 3 significant digits, 109 meters. Okay? 109 meters is about the length of a football field. Okay? So that's how long I would have to build this acceleration lane so the cars are going fast enough so that they can safely merge into traffic. So it'd have to be about a football field length, right? Now, you also want to play the what-if game. It's like, well, if I really want to be on the safe side and give grandma a lot of distance, I would assume maybe a slower acceleration of maybe 2 meters per second squared. Well, then I'm going to dividing by a smaller number. That would make my lane longer, okay? So that's what you want to be able to do, is play the what-if game. It's like, well, what if this acceleration was bigger? What if this acceleration was smaller? Now, I do want to point out one thing. Let's say that you want to solve this for v naught, okay? So you'd have v squared minus 2ad equals v naught squared. Obviously, you're going to have to take the square root of both sides. Now, when you take the square root of both sides, this is as far as you can go, okay? You cannot, do not go, oh, the square root of v squared is v minus, and I'm going to have v minus the square root of 2ad. Do not do this. You have to keep everything underneath this radical, okay? You have to keep everything underneath this radical, and then take the square root of it, okay? So be very cognizant of that, okay? All right. That's it. So let me hand out your assignment and then we'll go over that. Well, it makes it easier for me to keep track of, you know? Okay. So, on the back side of this, okay, when you work at a lot of assignments like this, where I'm giving you the sheet, okay, first off, treat this sheet as like a page in a textbook. You are not going to answer, you can write on this, you can do whatever you want, But at the end of the day, nothing gets answered on here. You're going to answer everything on another sheet of paper. Now, we haven't had this discussion yet because you have been doing this all like virtually. When and you've been great so far, but there's certain things that I hate, and they all start with FR. Freshmen, fractions, and frizzies. Okay, so like none of you have done this. I've had to threaten to kill some other kids. So like if you have a spiral notebook and you tear it out, the frizzies on the side make them go away. They're a train wreck. The papers all stick together. It's bad. Okay, so no frizzies. Don't write in pen. Thank God you all have been writing in pencil. Okay, so don't do anything in pen. So we've been cool with that. So and this is what I have on the back. So what you want to do is say, okay, here's your sheet of paper. You want to come over about a foot, a couple inches, not a foot. And you're going to draw a line. And you're going to put your answers on this left side, and you're going to put your answer and your work on the right side.
Does the red light mean it's working?
Yes.
Okay.
But I can't see the light from there. But next time I'm just going to ask you, hey, is the light flashing? Okay. So what you do is just like, God. All right. So, for example, like on your first 6 questions, those are all multiple choice. Okay? And you might not have anything to write. So you might go, okay, here's number 1, boom, here's your answer, number 2, da 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 da. Now, when you get to like question number 6, can an object move with uniform acceleration and constant velocity at the same time? Okay? Now, that's something that you have to explain. So you can carry that across both of these. Okay? So you're going to write out an explanation. So don't think you have to write everything in this column. You're writing out an answer. Okay? You can carry that across on both sides of this thing. Now, when you get to, like, let's say, for example, number 8, okay? So, what you want to look at on number 8, here's how I want this done. And I've shown you this on the back. First off, view this from my perspective, okay? My eyes are 54 years old. Don't blend all of these together. Leave spaces in between these problems. I want to be able to look and see what you have done. Now, if you get a problem like number 8, okay? So here's your line, here's number 8. If you want to do that V0, V dat, where you go in and you write down the variables that you have so you know what you have, fantastic, okay? That's great. I'd recommend it. You don't have to, okay? But that might be something that you consider until you get kind of a feel for how these problems are going to play out. So if you look on number 8, let's say you're going to do the V0 dat. So rocket this off its launch pad, okay? So when in doubt, here's a rocket, okay? So Brooke, what's the initial velocity of the rocket? 0. Oh, it's going to start at rest. Okay, so I've got my initial velocity. So it travels straight up, attaining a speed of 100 meters per second. Okay, so 100 meters per second, that's my final velocity. Okay, so I've got that. And then I've got a time of 10 seconds. Okay, so I've got my time. And then I want to calculate its acceleration. Distance, I don't care about at this point. Okay, so here's the deal. If you want to do that, that's fine. But what I do want to see is, hey, what equation am I going to use? Now, you only have 4 to choose from, okay? I have time, so I'm not going to use that equation. So I know, oh, okay, V equals V0 plus AT. Now, here's what I would recommend. And that, like I said, I've been doing these longer than you all have even thought about doing this, being on this earth. If you look at my answer key, here's the process that I go through. I write down the equation. I solve the equation. Oh, I want to get acceleration. So that's V minus V0 over time. Then I put in the numbers. Okay? That's the last step that I do. I worry about the numbers last. I ask myself, oh, it's speeding up. Okay, I have a positive velocity. Hey, I better end up with a positive acceleration. Okay? That's the thought process you want to go through. So you do this, trust me, you're going to get 100 meters per second minus 0 divided by 10 seconds, I get 10 meters per second squared. Okay? Now, again, view this from my perspective. I want to be able to see what you have done, okay? Now, here's what I'm going to tell you. When you get to number 9, leave a space, okay? Leave a space between 8 and 9 so that I'm not trying to figure out where problem number 8 stops and problem number 9 begins, okay? I want to be able to track what you have done if your answer is wrong. But I'm going to tell you this right now. If I don't see any equations and all I see are random numbers, I'm going to stop, okay? I'm going to. I mean, no offense, but I only have a certain number of hours left on this earth. And I'm not going to waste them trying to figure out what random numbers mean over there. If you choose not to keep your work organized, that's up to you. But my choice as the one who's grading it is saying, I'm not going to waste my time trying to give you any partial credit, and you're just going to miss all the points. That's the role. Y'all are big people, but that's the roll of the dice that you're all going to take. The reason that I do this, the reason that I work the equations and I solve them first, is because that's the best method. Okay? It's going to eliminate the mistakes. Pay attention to the units. Just don't go, oh, I'm just going to randomly put down numbers and then hope a miracle happens at the end, and then I'm going to get an answer. Notice that every time I work these problems, I put the units with it. Oh, I want an acceleration. Oh, that's meters per second divided by seconds. Oh, that's going to get me an acceleration of meters per second squared. Pay attention to the units as you go. Okay? So then you have number 9. Now, when you get to like number 11, okay? Number 11 has a whole bunch of different parts to it, A, B, C, and D. So when you get to one like number 11, do us a favor. Don't put like A, B, C, D. Don't put all of your answers here and then have all the work over here. You want to keep that answer beside that work, okay? So that way I'm here, I can look right over here and I can see that work that goes with it. So keep these answers beside the work that generates it, okay? Don't stack your answers up here and then have my work down here. Bad, okay? Worse yet, don't do this. Don't have your answer to be here and then draw an arrow and goes, oh, here's the work for part B. No, right away I will flip out, okay? Arrows are bad. Just keep the work right beside it. Now, when you get to number 11, I'm going to tell you, draw a motion diagram showing velocity vectors and an acceleration vector. What I want and here's what's happening on this problem. This gal is sliding into like second base, okay? So just draw V1. Now, here's what's going to happen with V2. One of two things is going to happen with V2. If she's going faster, draw V2 bigger, and the acceleration vector is going in that direction. If she's slowing down, draw V1 smaller and put the acceleration vector in the opposite direction. Okay, that's it. So draw V1 and then decide, is V2 going to be bigger? Oh, it's going to be going faster. Is it going slower? Then draw V2 smaller and make the acceleration vector go in the opposite direction. That's all you have to do. Now, I tell you, make a simple velocity time graph. If you want to draw that like on another sheet of paper, like on an actual velocity time graph, you can. If you just want to come over here on your paper and just make a simple sketch of this, go, oh, something like that, that's cool too. But if you're going to draw it on your paper, draw it big enough where you can label everything, and most importantly, my 54-year-old eyes can read what you've got. A lot of times on these velocity time graphs, I'm going to have some very specific instructions about what I want on the graph. So if you look on this one, I say on part B, on number 11, make a velocity time graph labeling the initial velocity, the time when she is stopped, and the slope of the line. So you want to have 3 things on that graph, okay? Clearly label what they are. Now, let's talk about number 17 on the back side. So if you read number 17, driver is traveling at 20 kilometers per hour and stops the car in 3 meters. Later, while moving at 40 kilometers per hour, same acceleration. So right away when you read number 17, what are you missing? What variable is missing? Time. So what are you going to use? that equation. So on 17, you're going to use that equation because there's no time involved. Now, you have 20 kilometers per hour. I want to make sure everybody's cool with this. You have to convert that kilometers per hour into meters per second. Remember, that's 20 kilometers per 1 hour. 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. So Matt, right quick, let's make sure everybody's cool with this. Basically, you're going to multiply by 10 and you're going to divide by 36 because you can lop off the zeros. So Matt, take 200 and divide it by 36.
200?
200 divided by 36.
Oh, okay. 5.56.
5.56. Now, here's the deal. When you do this conversion from kilometers per hour into meters per second, this has 3 significant digits. Keep 3 significant digits here. Do not round this to 6. Do not round it to 5.6. Okay? Keep at least 3 digits here. Okay? At least 3. All of your answers are going to have, if you look at all the data that I've given you, all these problems have at least 3 significant digits. So every one of your answers should have at least 3 significant digits. Okay? Now, I can preach up here, I can talk about these equations all day long, but until you really begin to use them, okay, that's when you're going to get a feel for how this plays out. So, like on 17, you're going to have 3 different parts to this answer. Okay? So you're going to have like 17A, boom, here's the answer for that. Then you're going to have 17B, and then you're going to have 17C. Keep these as separate entities. Now, let me give you a hint on 17. You're going to use that equation twice. The first time you use it is you're going to find an acceleration. Then on the second time, you're going to use it to find a distance. So on 17, you're going to use that equation twice. Okay? Now, when you get to number 10, okay? When you get to number 10, this is the space shuttle that's being launched, okay? And I'm going to tell you to make a sketch of a velocity time graph. Basically, you're going to have 2 points on this velocity time graph, okay? All I'm asking you to do is find the slope of the line, okay? You're going to have 2 x and y coordinate systems. You're going to have a time and a velocity here, and you're going to have a time and a velocity here. Find the slope of the line. Treat it like you're in a math class. Find your change in y, divide it by your change in x. Okay? Don't make that complicated. Okay? Don't make it complicated. Okay, I am done. So you have the rest of the time to work on this. If you have any questions, this would be the time to ask. Okay? So at this point, if you want to get your phones, if you want to listen to music, whatever, that's up to you. So tomorrow we'll do gravity. Wednesday we'll do a lab. Thursday we'll review. Friday's the test. So, all right. Live long.